Hey folks, welcome back to Bennett's Chemistry 12 tutorials. We're on to titrations in our last video for titrations, which the topic today is going to be titration curves, specifically for polyprotic chemicals, acids and bases. So let's just dive right into it because what we're doing, we've already done a bunch of titration curve things. So you're going to have to take a lot of the things that are in the previous 2 or 3 videos and kind of apply them to this one. Okay, so first of all, let's talk about what are we talking about when we're talking about polyprotic chemicals. So we're talking about polyprotic acids. So polyprotic means poly means more than one proton. So polyprotic, more than one proton. So you'd be talking about acids that have more than one H. Or if you were talking on the base side of things, you'd have bases that could accept more than one H. Those are generally indicated by having a -2 or -3 or -4 charge to the anion. Okay, so the typical ones that you might see, I'll give you just a couple of examples. So in terms of acids, maybe you would have common ones might be sulfuric, carbonic, oxalic is quite oftentimes used, phosphoric, which is H3, and another one that you might see quite commonly is citric acid, which has 3 H's. Okay, so there's some of the common ones that you might see. If we're talking about bases, maybe you'd be talking about CO3 -2 or SO3 -2 or well, it's C2O4 -2 or PO4 -3, so on and so on and so forth. Okay, so the acids, all of them have more than one H, and all of the bases, because of their charge, they accept more than one H. Okay, and so there are certain features that you're going to see in titration curves when you titrate these solutions of these types of things. There's going to be something very unique about their titration curve that you're not going to see in other titration curves for monoprotic species. Okay, so I'm going to go into a couple of things. Number one, what are those features going to be? And 2, why do you get those things? A little bit of the theory behind why they react slightly differently. Okay, why therefore you see these features on their titration curves. So I'm going to use an example of a diprotic acid, okay, and it doesn't really matter which one, so I'm just going to use just a generic H2X. So my example over here is, so we're going to titrate a diprotic acid, H2X, whatever that might be, with sodium hydroxide. And I'm going to show kind of the general shape of the titration curve over here on the graph of pH versus the volume of the, in this case, sodium hydroxide that we're adding into it, okay? I haven't done any specific calculations. I haven't got any specific numbers in there, but you're going to see kind of relatively what you're looking for, okay? Okay, so because this is a diprotic acid, the solution would have an initial pH, which would be somewhere in the acidic range. So I'm just making stuff up here. So let's say it's down here around, has an initial pH down there around 2.5-ish, somewhere around there. Who knows? Okay, that would obviously depend on which diprotic acid this was and what the concentration of it was, and that would give you whatever that pH is going to be. Okay, so then we start doing our titration. Now, as would be typical, if this was a strong acid, if H2X was H2SO4, the only diprotic strong or polyprotic strong acid, then what you would expect to see is you would expect to see this just come straight out. There wouldn't be any kind of a buffer zone, if you recall, with weak acids. So let's pretend this, whatever H2X is a weak. So what that would mean is you would probably see a little rise right off the bat and then a plateauing effect as you start doing the titration. Okay, so leveling off. Still changing, still rising ever so slightly, but there's a buffering effect, right? And that's where the addition of more base there's going to be a resistance to change in that pH because you're creating a buffer solution. Now, I'm going to stop right there. I'm just going to draw the beginning of this curve because I want to get in a little bit of the theory. So I've got over here, I've got a picture of an Erlenmeyer flask, and in there I've put 5 molecules of H2X. Obviously, this is just for me to demonstrate the point. There's more than that, obviously. So H2X molecules are floating around, and they are the number 1 acid that's in there, okay? Of course, it is doing an equilibrium, and there's some other things that are present in there. But we're going to talk in a simplified form here. So I've got 5 of these H2X floating around in there. Let's pretend I drop in, if I could, 1 molecule of NaOH. Just 1. What is it going to do? Well, it's going to go in, and because it's a base, it looks for, it doesn't look for, the probability is that it is most likely to pick up an H from the thing in that solution that is the most willing to give up the H. The thing that is most willing to give up the H would be the strongest acid that's floating around in that water. The strongest acid that's floating around in that water, well, what are the options? Well, there's water molecules, H2O. There's H2X's that I've drawn up here. And then if you're thinking kind of back when we were doing polyprotic acids way back in the acid-base unit, there would be some HX minuses floating around in there because of the equilibrium that is in there. But really, I mean, that's the third option, but by far the strongest acid that's in there are actually molecules of H2X. So when a single NaOH goes in there, just think, 1 molecule, what does it do? It's going to react with one of the H2X's because it's the strongest thing in the water. And so when it does that, 1 NaOH with 1 H2X, the NaOH has the ability to pull up 1 hydrogen off of that acid, which means it's going to form, the OH will take 1 hydrogen from the acid and form water, and then leave behind HX minus. So there's still another H left on that thing, so it's HX minus. So I drop in a single NaOH, and it changes, okay, and so I'm going to use different colors, and I apologize if you happen to be red-green colorblind, I apologize. H2, it'll take one of these and change it into HX minus. So now there's 4 H2X's and there's 1 HX minus floating around. I add a second NaOH into there. And what does it do? It pulls an H off of the strongest available acid. Well, okay, now we've got some choices. We've got water, we've got H2X, and we've got that green HX minus that's floating around in there. But since there's lots of H2X's around, the NaOH is most likely to react with the H2X. So do this neutralization again. And so what happens is maybe this guy gets converted into an HX minus. And so it did this reaction with the NaOH that we dropped in there. We add a third NaOH and a third H2X. Reacts, because again, H2X is still the strongest acid that's floating around in the Erlenmeyer flask. So far we've added 3 NaOHs, we've removed 3 H2X's. And so what hopefully what you're starting to see is you're going to get rid of all of the first hydrogens off of your diprotic acid before the second H is going to be removed, because NaOH is going to react with the acid that is most likely to give up the H. And so what happens is we'll add a fourth one, and we'll be there. Now, what does this look like on our graph? Okay, so we're adding NaOH so far, right? We're dribbling it in. We're adding the titrant over here. So we're adding and adding and adding, and as we're adding it, we're making more HX minuses, and we're removing H2X's. So what we're doing is we're going through the titration. There's a little bit of a buffer zone, and then all of a sudden what happens is you're going to start to, like where we are right now, where we're down to, well, we've removed 4 out of the 5 H2X's and kind of turned them into HX minus. We're starting to see a little bit of a rise in the curve. In your brain, you're thinking, ooh, I wonder if we're about to like hit the super steep, we're at equivalence part of our titration curve. So when is equivalence going to occur? Well, if I add a 5th sodium hydroxide into here, well, guess what? I am getting rid of every speck of that H2X. And so what I've now done is I've taken all of the H2X, I've turned it all into HX minus before any of the HX minuses were actually touched. Okay, now again, I'm simplifying it, okay, to keep this nice and very compartmentalized. Okay, so the HX minuses are now all floating around. But what you're going to see on the graph is you're going to see a little steep section. Because now I've got all HX minuses, I don't have a very good buffer solution because I don't have a partner to the HX minus. I don't have any H2X's anymore because I forced them to react with the sodium hydroxide, nor do I have a lot of what HX minus would form if it was an acid, X minus 2. So I do not have a very good buffer solution, and therefore you're not going to see any plateauing on the curve. You're actually going to see it kind of have a bit of a sharp rise. However, I don't know we've reached this point because all I'm doing is I've got a pH probe in there and I'm just titrating as we go along. So when you're doing a titration curve, you just add the sodium hydroxide, then you just keep going. You keep adding, keep adding, keep adding. Well, if I add one more sodium hydroxide into my Erlenmeyer flask over here, one more sodium hydroxide, what it's going to do is it's now going to not react with any H2X's, so I don't have any H2X's anymore. It's going to react with HX minus. And we're going to form H2O. Okay, so the NaOH and the H from the HX minus are going to form water plus X minus 2. I took that last hydrogen off of there, which means I've taken this guy and I've now removed the final H, and now it's X minus 2. Now what I start doing is now I'm forcing the HX minus to turn into X minus 2. I'm actually creating an actual buffer solution of HX minus and X minus 2. I'm creating a new buffer solution. So what you're actually going to see on the curve is, and this is kind of an interesting thing, is this is going to start to bend again. It's going to start to plateau again. Just like quick rise here, then a plateau, because there was a buffer solution between H2X and HX minus. Buffer solution. Then we got rid of all the H2X, so we got rid of that buffer solution. But then we started creating another one. I add another sodium hydroxide. And I get rid of another one of these. And I turn it into X minus 2. The buffer solution gets even better. And so it continues on. Now, this feature that you're going to see with diprotics and triprotics and everything like this is you're going to see every time there's an H that comes off of an acid when you're doing a titration, you're going to see a rise and then you're going to see a replateau. So essentially what you're going to see is you're going to see the number of H's on the acid will equal the number of rises in the titration curve. Okay, so this first rise right there is indicating there was 1H. But because it replateaued, and we're nowhere near, like way up into the base zone where a regular titration curve would be, this is telling us, ooh, there must be another H to remove off of this acid. Okay, we're not done yet. And so you keep adding and adding and adding. This first rise right here, the middle of the steep section, okay, so I'll put a little dot on there. That middle of the steep section is known as the first equivalence. Now, if you had an indicator in there or you weren't paying attention to what the curve was doing as you were titrating this thing, you wouldn't even notice this thing. Like like so, right? There's a little rise in the pH, but you wouldn't see it from a color change. You wouldn't know any of this unless you kind of stopped and looked at your titration curve as you were doing this. You wouldn't notice this thing. So this guy right here, that guy right there is called the first equivalence point. And the fact that it's replateauing is telling me there's going to be at least a second, maybe a third, maybe a fourth. I don't know. I don't even know what this acid is. Let's pretend we don't know what this acid is. Now, I want you to think of the stoichiometry here. It took, way back to my original example, it took 5 sodium hydroxides to get rid of all the H2X's, to turn them all into HX minus. That happened, we reached the first equivalence point. Then we started adding more NaOHs to get rid of the HX's, turn them into X minus 2s. How many HX minuses were there? Well, 5. Because I started with 5 H2X's, they got all converted into HX minuses, so there's 5. So I have to turn all 5 of those into X minus 2s before I reach the next equivalence point. 5 to the first one, 5 to the second one, which means on my graph, if I'm right here, I'm looking at about, I'm guessing, it's about 10.5 mils. About 10.5 mils, that means that the second equivalence is going to be twice that. Right? If it took 10.5 to get here, it's going to take another 10.5 to get to the next one, which means it's going to be at about 21. So it's going to be somewhere on that line. So you keep titrating, and you get rid of a third one, and it turns into X minus 2. And you get rid of a fourth one, and it turns into an X minus 2. Remember, we're getting really close at this point, right? I've only got one more sodium hydroxide to add in. So what would I see in my curve? Well, I'd see we're starting to lose our buffering capacity again. Okay? Then I add the fifth one, okay, the critical, the final one. And I'm down to all of my X minus 2s. So the X minus 2s are now what you have in the solution. A couple things about the X minus 2s. Do I have any molecules in there, like the HX type of molecules, that can take a sodium hydroxide and donate an H to the sodium hydroxide? The answer is no. Right? All I've got in there now is water molecules. So essentially, once we get to the point where they're all turned into X minus 2s, we're done. Okay, so it's actually called the final equivalence point, or final endpoint if you're talking about a color change, right? So that final endpoint is when, okay, you can add more sodium hydroxide, but there's no acid molecules remaining in there to actually donate to that base that you've added, which means now it's going to shoot up into that basic zone, right? So now, once we go past this final endpoint, we're just adding sodium hydroxide into the beryllium iron. We're just making it more and more basic. So what you will see on the curve is you will see a rapid rise, and then you'll see plateauing out up at the top. The final equivalence point will occur once the solution then is just, it plateaus out here, and then you can add as much base as you want. It will go a little bit higher, but it will never go beyond whatever the sodium hydroxide concentration was. Okay, it'll go up to whatever that pH would have been. And so when you see this curve, you'll see a couple of things. Number one, the number of rises, steep sections on the curve equals the number of equivalence points. Okay, and those equivalence points are always equidistant along the x-axis, meaning the volume of the titrant that you're adding. This distance here from 0, from the initial to the first equivalence, will equal the first equivalence to the second equivalence. And every time that you have another equivalence point, that distance should always be the same. Should always take the same volume to get to the next equivalence point. So the volumes will be the same, the number of rises will be the number of equivalence points, and the number of equivalence points equals the number of hydrogens on the acid. Okay? So if this thing was a truly unknown acid, and I did a titration curve, the reason why I would do a titration curve is the very first thing I would see when I do the titration curve is the acid monoprotic, diprotic, triprotic, whatever it would be. If this was a monoprotic acid, I wouldn't see the two steps. I wouldn't see the two rises in it. I would only see one rise, and then it would be monoprotic. If it was a triprotic acid, how many rises would I see? Well, I would have seen 3, and they all would have been equidistant apart. And so I would have seen that in the graph, and I go, oh, my unknown is a triprotic acid. That certainly limits the field of possibilities for what the thing could be. I mean, if you see a graph like this, we already know it's limited. We know it's limited because we're only talking about a diprotic acid. All the monoproducts are thrown out. All the triproducts are thrown out. This thing's a diprotic acid. Then what you can do is you can do a whole bunch of things, because now I have data from my graph. So what types of things do I know? Well, I know the final endpoint. And typically when you're titrating, you know you're going to the final endpoint where that pH, it shoots up and it's in the base range and you're done your titration. That final endpoint, we would have used phenolphthalein, because phenolphthalein would have changed right in that range. The final endpoint is when you get to the last stage. Okay, so over here on this, the neutralization, notice how I demonstrated it in 2 very distinct steps. Right? There's like, the first step was taking off all the H's from H2X. The second step was taking all the H's off the HX. And we started with all of this, but we finished with all of that. And we weren't done the titration until it was all X minus 2. Well, do the math on this, okay? And think back to your reaction mechanisms way back in your beginning of the course. HX right here and HX right here cancel. And it gives you an overall equation of H2X plus 2 NaOHs go to 2 waters and X minus 2. Well, I guess it should actually be. It's the sodium salt of that, so it's Na2X. And that's the overall, which is a balanced neutralization equation when the acid is a diprotic. It takes 2 sodium hydroxides. But it kind of, when you're doing the titration, it kind of happens in 2 individual steps, because H2X and HX minus are different strengths. They give up their H's differently. And so you actually see that on the curve. And it helps you identify what that unknown is. Now, if this was a base, let's say I was titrating CO3 negative 2, and I'm titrating it using a strong acid, what you would have seen is something very, very similar. You would have seen 2 steps, but they would have been downward steps. Rather than a staircase going upwards, this would be a downward step. So it would have started up here somewhere, because CO3 negative 2 is base. It would have plateaued, it would have dropped down, it would have plateaued, and then it would have dropped down, and you would have had your final endpoint, because CO3 can take 2 H's. If it was PO4 negative 3, you would have seen 1 drop, 2 drops, 3 drops, because it can pick up 3 H's. Okay? So titration curves are very useful in identifying if you have a truly unknown substance. The very first step is do a titration curve so that you know if you're talking mono, di, or triprotic, whatever it is that you're talking about. Then you can actually take it a step further. Now, of course, we know the volume, it took 21 milliliters. If we happen to know the concentration of the sodium hydroxide we were adding in, we now know concentration times volume would give us moles. We know it's a 2-to-1 ratio over here. We would know the moles of the H2X. We could figure out what the initial concentration of the H2X was from that neutralization equation and the data coming off of the curve. Once we know the initial concentration of the H2X, we also know what pH that thing was producing right off the bat. So we could actually calculate the Ka of H2X and know that it's diprotic. We would then have its Ka, and we'd be able to identify that thing. Okay, so that's the titration curve information stuff for polyprotics. You can take that information with you in terms of laboratory things, or also if you're doing calculations as well. So next class, we are done the titration stuff now. So now we're into reduction oxidation. So that will be the last unit of Chemistry 12. It's a pretty big one. So there's multiple videos for that one. But we'll see you next time, and we'll do the introduction to what reduction oxidation is and how it applies and what the basic theme of redox is. Okay, we'll see you then.